Okay, so for section 6.3, we are going to talk about the definite integral. In section 6.2, we talked about the indefinite integral. So we added a plus c, our integration constant. And so now we are going to work through some stuff where we don't need to do that. But first, we're going to start talking about area. So what I have right here is the function 3 minus x just from the interval 0 to 3. So we're looking at this area right here. And so what's the area between the graph and the x-axis? So I'm going to count boxes. So we have 1, 2, 3. This would make 4.5 boxes. So we have 4.5 boxes. That is actually the area here is 4.5 units squared. If you wanted to do the area of a triangle, remember is 1/2 base times height. What is the base of this? Well, that would be 1, 2, 3. The height is also 3. So 9/2, which is 4.5. Okay, so we also can use the antiderivative to find the area, and that's kind of cool because we can do this for shapes other than triangles. So we're going to use this triangle to show that that actually works. So the antiderivative here, capital F of x would be 3x minus x squared over 2 plus some constant c. So increase and divide for each of those. Number 2 says to find f of 3 minus f of 0. So f of 3 would be 3 times 3 minus 3 squared over 2 plus c. And then f of 0 would be 0 minus 0 plus c. So f of 3 minus f of 0 would be 9 minus 1. Oh, that's a 2. Why did I write a 9 right there? Anyone know? No, that's a 2. 9 minus 9/2 plus c minus 0 plus c. All right, so those plus c's are going to go away. 9 minus 9/2 would be 18/2 minus 9/2, which is 9/2, which is good because that's what we got before. So this shows you that the antiderivative on a certain interval will give you the area between the graph and the x-axis, which is cool. So this is useful, like I said, for things that are not triangles, but like this piece of a parabola here, we can do the area of that as well with the antiderivative. So we can estimate it by like counting. So it looks like it's a little more than a half and a little more than half. So the area is probably a little more than 1. But let's actually find that. So if we do the antiderivative, we would have x minus x cubed over 3 plus c. And then we're going to look at f of 1, which would be 1 minus 1/3 plus c. F of negative 1, which would be negative 1 plus 1/3 plus c. This is 1 minus 1/3 is 2/3 plus c. And then this would be negative 2/3 plus c. So f of 1 minus f of negative 1 would be 2/3 plus c minus negative 2/3 plus c. So distributing that minus, the c's would go away, and that would become 2/3 plus 2/3, which is 4/3, which is a little more than 1. So that's good. So the definite integral is just that. Instead of last time, we basically had the integral without these limits on it. Now we're going to have limits on our integration. So we're just looking at the interval from a to b and doing the integral on that piece. And so that is equal to f of b, the antiderivative at b, minus the antiderivative at a. I'm going to often write this as like this in between step. I'll write this as the antiderivative, and then I'll put this vertical bar and go from a to b. And then that would be f of b minus f of a. Okay. So that is if f is continuous on a, b, and f is any antiderivative of f. This means we don't need the plus c. They're going to cancel anyway, like we saw in those examples. So we don't need it. Okay. So when f is above the x-axis, the definite integral is the area between the graph and the x-axis. If it's below some, like say it was like this, the integral would give you 0 because this will count as negative area and this would count as positive area. So the integral would be 0. Say this is a to b here. This would be 0. But if you actually wanted the area, it would be, you wouldn't do the integral because of this negative bit. You'd have to break it up, and we'll talk more about that later. So when it's above the x-axis, it does give you area between the graph and the x-axis. Okay, so let's do some practice. We're going to look at the integral from -1 to 0 of 5x squared. So this would be equal to the antiderivative of that, which would be 5x cubed over 3. And we're going to evaluate that from -1 to 0. So this would be 5 times 0 cubed over 3 minus 5 times -1 cubed over 3. So f of b minus f of a, top minus bottom here, or end minus beginning for your interval. So that would be 0 minus -5/3. So that would be +5/3. Number 2, we have the integral from 1 to 4 of 1 over x dx. So this is going to be equal to the antiderivative. So that's the ln of absolute value of x. And we're going to evaluate that bottom to top here. Top minus bottom, sorry, I can't draw a straight line. There you go. 1 to 4. So we're going to do the ln of 4 minus the ln of 1, top minus bottom. This is actually equivalent to ln of 4 over 1. We don't need absolute values because those are both positive. This is equivalent to the ln of 4 over 1. Division outside of subtraction outside, you can do division inside. So it's just the ln of 4. Okay. The antiderivative, or the integral from 0 to 3 of 1 plus e to the x dx. We're going to take the antiderivative. So that would be x plus e to the x, and that's all we need there. And then this we're going to evaluate from 0 to 3. We're going to do top minus the bottom. So 3 plus e cubed minus 0 plus e to the 0. So 3 plus e cubed minus 0 minus e to the 0 would be 1. So 3 minus 1 is 2. So 2 plus e cubed. All right. Number 4, we have the antiderivative, or the integral from 3 to 5 of 1 over x minus 2 dx. So we can actually do this. This would be equal to the ln of x minus 2. Since the derivative of that is just 1, we were fine to just do that. And then this we're going to evaluate from 3 to 5. We're going to do top minus bottom. So the ln of 5 minus 2 minus the ln of 3 minus 2. So we have the ln of 3 minus the ln of 1. We don't need those absolute values anymore. This is the ln of 3 divided by 1, which is just the ln of 3. All right. We keep going. Examples, the square root of x. So we're going to do increase. That is, remember, this is the same thing as the integral from 1 to 9 of x to the 1/2 dx. So we're going to increase and divide. So increase to 3/2, divide by 3/2, which is the same thing as multiplying by 2/3. And then we're going to evaluate this antiderivative from 1 to 9. So we have 2/3 times 9 to the 3/2. That's the top part minus the bottom, which would be 2/3 times 1 to the 3/2. The square root of 9 is 3. Cubed is 27. So 2/3 times 27 minus 2/3 times 1. That's 26 times 2/3, which is 52/3. 27 times 2/3 minus 1 times 2/3. So that is 26 times 2/3. Just do this in your calculator, but I don't have one right now. 26 times 2 is 52 divided by 3. Okay. On this next one, we have, this is the same thing as the integral from -4 to -2 of x to the -2 dx. So we're going to increase and divide. I'm going to put a line here. I'm going to squish this up. Maybe change colors to get something else going on here. Okay. Let's change colors too. All right. So we are looking at, this is the integral from -4 to -2 of x to the -2 dx. So we're going to rewrite that. I mean, we're going to actually increase and divide now. So increase to -1 and divide by -1 or multiply by it. And then we're going to evaluate that from -4 to -2, top minus bottom. So we have -1 times -2 to the negative. Ugh, I hate this. Let me rewrite this first. There's too much happening there. We'll write this as -1 over x, evaluate it from -4 to -2. All right, so then we have -1 over -2, top minus bottom, -1 over -4. So we have 1/2 minus 1/4. That's 2/4 minus 1/4, so 1/4. Okay. Let's keep going. This integral down here, let me get a line there too. Looking at this integral, we're going to increase and divide. So 4x squared over 2 plus x. And we're going to evaluate that from -1 to 3. I'm going to simplify before I do that. So I have 2x squared plus x, evaluate it from -1 to 3. I'm going to do top minus bottom. So 2 times 3 squared plus 3 minus, and notice I'm putting the whole second piece in parentheses so that I remember to apply that negative to everything over there, that minus sign. Okay, so 9 times 2 is 18 plus 3 minus, that's 2 minus 1. So 21 minus 1, which is 20. That matches what I have. All right, which doesn't say much of anything, except I did the same thing twice. Number 8, I am going to take that 4 out of the integral. Remember, that's a thing that we can do, and it's just going to make the what I'm looking at easier to digest here. So this would be 4 times the ln of absolute value of x plus 3, and we're going to evaluate that from -2 to 1. And we're going to do top minus bottom. So 4 times the ln of 1 plus 3 minus 4 times the ln of -2 plus 3. So this is 4 times the ln of 4 minus 4 times the ln of 1 which is equal to 4 times the ln of 4 minus the ln of 1, which is 4 times the ln of 4 over 1, which is 4 times the ln of 4. All right, so number 9 opens up a whole new, you can see 9, 10, and 11, and 12 have a lot more stuff going on. They're all going to require you substitutions to do the integrals. So I'm going to do that stuff in like green here. The inside function here is e to the negative 1.5x. This is u. Ooh. So du is e to the negative 1.5x times negative 1.5 dx. Oh, sorry, that isn't the inside function. The inside function is just the exponent of the negative 1.5x. That makes more sense. Then du is negative 1.5 dx. So we're going to divide by that. That is negative 3/2 dx. So then if I multiply by negative 2/3, that would work. So negative 2/3 du equals dx. So what I'm going to do is pull that 2 out. I have the integral from 1 to 3 of e to the u, and then times du, but the du here is negative 2/3 du. So replacing this with u and the dx with negative 2/3 du. So I should have actually written a du. There we go. And then that negative 2/3 I'm going to pull out too. So I'm looking at negative 4/3 times the integral from x equals 1 to 3 e to the u du. And that's important. So sometimes I don't do this when I'm teaching this, but some people will teach you to actually convert your limits to be in terms of u instead of x. I'm going to do the integral with u and leave the limits alone and then convert back to x at the end and plug in those limits. Some people will teach you to change the limits so that you don't have to do that. It's, 6 dozen of one or 6 of one and half a dozen of the other. So do what works for you. But this makes more sense to me. So I am going to evaluate this. E to the u, the integral of e to the u is just e to the u. That negative 4/3 is still there. And this is from x equals 1 to 3. So I'm going to put this back in terms of x. So negative 4/3 times e to the negative 1.5 x. Then evaluate from 1 to 3. And I should have left myself more space to do this. Let's see. Oh. Okay. When I plug in 3, so I have negative 4/3. I'm just going to put on the outside, and then do this part. I shouldn't use that color. Just do this. So I would have e to the negative 1.5 times 3 minus e to the negative 1.5 times 1. And then that is negative 4/3 times e 1.5 times 3 is 4.5 times 3 is 4.5. So e to the negative 4.5 minus e to the negative 1.5, and just leave that there, or get a decimal approximation. Like I said, I don't have a calculator on me, so that one's kind of messy. Let's try another one with u substitution and see how it goes. So the inside function here is 3 minus 2x. So u is equal to 3 minus 2x. du would be negative 2 dx. So negative 1/2 du, we're going to substitute in for dx. So we have the integral from 2 to 3 of u to the fourth. This is x equals 2 to 3 of u to the fourth times negative 1/2 du. So I personally will pull that 1/2 out. So negative 1/2, the integral from x equals 2 to 3 of u to the fourth du. This would be negative 1/2 times u to the fifth over 5. Evaluate it from x equals 2 to 3. U is 3 minus 2x. So we have negative 1/2 times 3 minus 2x to the fifth over 5. Evaluate it from 2 to 3. Boom. So negative 1/2 on the outside. And then this part will be with the 3, and then minus this part with the 2. 3 minus 2 times 3, that to the fifth over 5, minus 3 minus 2 times 2 to the fifth. There's so many parentheses here, over 5. Negative 243. This is what I have, over 5. And then plus 1/5. So negative 1/2 times negative 242 over 5, which is 121 over 5. You can absolutely use a calculator for doing like this sort of math. Okay. Let's see if I can condense that and make that look nicer for when we do the second part now. I mean, the next problem. Thankfully, there's no other part to that problem. All right. Oh, no. Okay. On this next one, the inside function u is x squared plus 4. Du would be 2x plus 0 dx. So we have x dx, so I am going to get that 2 to the other side. So 1/2 du is x dx. And now we're ready for that substitution. So this is the integral from 0 to 2 of 1 over the cubed root of u times x dx, which is equal to 1/2 du. This is x equals 0 to 2. So the 1/2 I'm going to take out. I have x equals 0 to 2 of u to the negative 1/3 du, which is going to be increase and divide. So u to the 2/3 divided by 2/3 would be multiplying by 3/2. There's already that 1/2 out there. And then this is going to be evaluated from x equals 0 to 2. So 3/4 u to the 2/3, evaluate it from x equals 0 to 2. Plug in what u is. So 3/4 times x squared plus 4 to the 2/3, evaluate it from 0 to 2. When you do this in a calculator, wait, let's see. I'll have this up here. Uh-oh, pulled off that X there. And what else did I do? That. Okay, I think everything went. So then coming back down here, I have the 3/4 on the outside, and then I'm going to evaluate with the X equals 2 here, minus this thing evaluated when X equals 0 here. So when you plug in 2, you get 2 squared plus 4 to the 2/3. And here you get 0 plus 4 to the 2/3. So we have 3/4 times 8 to the 2/3. That would be 4. 8 to the 2/3 minus 4 to the 2/3. I have this as equal to approximately 1.1. All right, and then number 12, before we start average value, is going to be, maybe I'll start that in another video. Number 12, the inside function here is u equals x squared minus 1. Du would be 2x dx. So 1/2 du is equal to x dx, because that's what I actually have is x dx. So this would be the integral from x equals 1 to 3 of e to the u times 1/2 du. So that's 1/2 times the integral from x equals 1 to 3 of e to the u du, which is just 1/2 e to the u, evaluated from x equals 1 to 3. We're going to plug in our what u is, which is x squared minus 1. That'll be evaluated from x equals 1 to 3. So we have 1/2 e to the 9 minus 1 minus e to the 0. So that's 1/2 e to the 8th minus 1. Works for me. All right, I'm not going to start this in another video. It's not that much stuff. So the average value is an application of derivatives, of antiderivatives, definite integrals, because that's the section we're in. Suppose you bought 3 pairs of shoes for $37, $58, and $62. What's the average cost of the shoes? So you would do 37 plus 58 plus 62 divided by 3. The average cost of the shoes is $52.33. For a finite number of values, we can find the average like we just did, but what about for an infinite number of values like with a function? So we're trying to find the average value of a function on the interval from 0 to 8. So we can do what we did there, just sort of take a bunch and average them out and say, maybe it's this. So f of 0 here is 0. F of 2, if you trust me on this, is 12. F of 4 is 16. F of 6 is 12. I don't trust myself on that one, but okay. Oh yeah, that makes sense. So it go back down. We divide this by 4, we get the average value of those is 10. So if we do this again with 1, 3, 5, and 7 instead of our for our x values, so f of 1 is 7, f of 3 is 15, f of 5 is 15, and f of 7 is 7, and we divide by 4 again. We actually get 11 this time. So it does matter what values that you pick. Those are close though, so that's good. We could get a better estimate by taking more values, right? So think about, okay, I have a bunch of x values. I'm going to take the function values at all of those, n of them, say, and I'm going to divide by n. This would get me an average, a guesstimate, right? This is going to be a guesstimate. We'll say estimate, that'd be better. So this would be better, right? The more times I pick off the y value and average it out, then the closer I'm going to get to the actual average. That means we can get an exact value of the average by taking a limit as n goes to infinity. Turns out this is the definite integral. So you would take the average value here. You would do 1 over b minus a. That would be the n here. Hold on, let me write this differently maybe. So you do the integral from a to b of f of x dx, and then divide by b minus a, because that would be your span. That's your n. So oftentimes we're going to write that as 1 over b minus a. So however long your interval is, so b minus a, and then the definite integral from a to b of f of x dx. That is the average value. And again, that makes sense if you're thinking about taking the adding up a bunch of these and then dividing by n. This is us adding up a bunch of them. This is dividing by n. All right. So that's the average value. So let's do that for some examples. So the average value of this, the average value, that means I'm going to do the integral on that interval, but I'm going to divide by the length of the interval. So average value would be 1 over b minus a times the integral from a to b of x squared plus 6. So this would be 1/3 times the integral from 1 to 4. Actually, I can go ahead and do that. That would be x cubed over 3, increase and divide, plus 6x. And this is going to be evaluated from 1 to 4. Leave that 1/3 on the outside and do 4 cubed over 3 minus 24, 6 times 4, minus 1/3 plus 6. This gives you 13. All right. Do that in a calculator and make sure that I am right about that, but I'm pretty sure I am. All right. Number 2, we're going to do the average value again. So the 1 over b minus a, so 8 minus 3, times the integral from a to b, so 3 to 8, of x plus 1 to the 1/2 dx. So this is going to be 1/5 times x plus 1 to the 3/2 times 2/3. Evaluate it from 3 to 8. So you're looking at 2/15 times this thing. So 8 plus 1 is 9 to the 3/2 minus 4 to the 3/2 times 2/15. Oh, I don't have an answer for that. But y'all can do that in a calculator. And then the same thing on number 3. We are going to do the average value. So 1 over b minus a times the integral from a to b of the function. And then hopefully we can work this out. That would be 1/4 times increase and divide minus increase and divide plus increase and divide. And that is evaluated from -1 to 3. Plug that in and see what happens. Again, you're going to have to show your work here. So your calculators can absolutely check the stuff for you, though, and you should be doing that. And if you need to see that, then just let me know. I can help you with it. But anyway, this is what you should do. And so that's average value. Take the integral from a to b and then divide by the length of the interval. So that is section 6.3. You guys let me know if you need any help with anything. Thank you.